The James Webb Space Telescope has now shown us something that fundamentally changes how we understand the scale and age of the universe. When it looks at patches of sky that appear completely dark to every other instrument humanity has ever built, it finds hundreds of thousands of galaxies. Fully formed, actively star-forming, chemically mature galaxies that were not supposed to exist at all in those early cosmic epochs. And the deeper the implications of these discoveries sink in, the clearer it becomes that almost everything we once assumed about cosmic structure, cosmic timing, and the observable limits of reality itself requires serious revision. For most of modern astronomy, cosmologists worked from a carefully constructed picture of how the universe grew from simple beginnings into complex structure. The Big Bang produced an almost perfectly uniform distribution of matter and energy. Tiny density variations existed across that early universe, regions fractionally denser than their surroundings. But gravity, though powerful, was expected to work slowly. Those slight overdensities would pull matter toward them across hundreds of millions of years, gradually accumulating enough mass to trigger star formation, then galaxy formation, building complexity through patient incremental steps. In this framework, the first stars were not expected to ignite until several hundred million years after the Big Bang. The gas needed to lose energy and cool sufficiently before it could collapse under its own gravity. Dark matter halos needed time to accumulate enough mass to gravitationally trap ordinary matter. After stars finally formed, they needed to live out their full lifetimes and die before the heavy elements forged in their cores could enrich the surrounding gas. Each stage imposed a minimum timescale. Compress the sequence too aggressively, and the physics simply stops working. The universe, according to every model refined over decades of theoretical work, was supposed to learn to walk before it learned to run. That expectation shaped what astronomers anticipated finding when the James Webb Space Telescope first began surveying the cosmos as it existed billions of years ago. They expected scarcity. A few primitive, dim, fragile galaxies scattered across the ancient sky, barely holding themselves together in a young cosmos still finding its organizational footing. What Webb found instead was crowds. Survey after survey returned the same surprising result. Bright galaxies appearing in cosmic epochs that standard models had predicted would be nearly empty. These were not faint sparks barely maintaining structural coherence. They were already active, busy systems producing stars at rates comparable to or exceeding those of much more mature galaxies from far later eras. The surprise was not isolated. It was not one anomalous object defying theory, while everything else behaved as expected. It was a pattern, consistent across different surveys, different regions of sky, different observing wavelengths, and different analysis techniques. Webb detected galaxies within the universe's first 500 million years that contained hundreds of millions of stars worth of matter. Others appeared to hold billions of stellar masses. The sheer quantity of material assembled in such a short time were genuinely troubled cosmologists, because gravity, however powerful, is not instantaneous. Building a galaxy of that mass requires a sequence of steps, and each step takes time. Gas must cool and collapse. Dark matter halos must grow. Stars must ignite and burn through their fuel. Some of those stars must die and seed their surroundings with heavier elements before the next generation can form. There is no shortcut through these processes, and yet Webb's observations implied that the universe had somehow accelerated through all of them far faster than any model allowed. One of the most telling pieces of evidence was not just the mass of these early galaxies, but their elemental composition. Webb carries instruments capable of spectroscopy, the analysis of light wavelengths, to determine which chemical elements are present in distant objects. When astronomers applied this technique to galaxies formed just a few hundred million years after the Big Bang, they found clear signatures of carbon, oxygen, nitrogen, and other heavy elements. This observation carries an unavoidable and deeply significant implication. The primordial universe contained almost exclusively hydrogen and helium. Every heavier element in existence must be manufactured inside stars through nuclear fusion, then released when those stars die. Carbon, oxygen, and nitrogen inside an early galaxy means that at least one prior generation of stars had already completed its entire life cycle. Stars had formed from primordial gas, burned through their nuclear fuel over millions of years, and ended their lives in explosive events that scattered heavy elements into the surrounding interstellar medium. All of this had already occurred within the universe's first few 100 million years. The cosmic timeline was being compressed into a far shorter period than any model had allowed. To understand why this troubled astronomers so fundamentally, consider an analogy. Building a city requires sequencing. You cannot construct skyscrapers before you have roads to transport materials. You cannot pour concrete before steel reinforcement exists. You cannot install electrical systems before electrical infrastructure has been established. Each stage depends on completing the stages before it. The process has an inherent order that reflects real physical and logistical constraints. The early universe was supposed to be laying foundations, preparing groundwork for more complex structures that would emerge later. Webb found finished buildings standing tall, their construction completed far ahead of any reasonable schedule. This growing contradiction between prediction and observation became known among cosmologists as the impossible early galaxy problem, or the too much too soon problem. When astronomers calculated how much total light galaxies should collectively produce during the universe's first billion years based on standard models, their predictions consistently fell short of what Webb actually measured. Webb's observations exceeded theoretical predictions by factors of 2, 5, and in the most extreme cases, by a factor of 10. That magnitude of discrepancy is not a calibration error or a rounding issue. It is a clear signal that something fundamental about the underlying model is incomplete. Scientists responded with exactly the kind of systematic skepticism that defines rigorous science. They questioned the measurements themselves, rechecking Webb's instruments for systematic errors and calibration problems. They considered whether dust, which can both absorb and redirect light, might be making galaxies appear brighter than they truly are. They investigated whether gravitational lensing, where massive foreground objects act as natural magnifying lenses for background galaxies, could be inflating the apparent brightness of distant objects. After exhaustive analysis, the results held. The early universe was not dim and tentative. It was luminous and active. Some of the most extreme early galaxies were briefly described by researchers as universe breakers, objects whose existence appeared to violate the fundamental limits imposed by cosmological models, objects that simply should not exist at those ages if standard physics was complete. Initially, some astronomers hoped that the mass estimates for these objects were being systematically overestimated. Perhaps the brightness of early galaxies was being inflated by contributions from supermassive black holes at their centers, massive engines of radiation whose output could make a galaxy appear far more luminous and apparently massive than its stellar population alone would justify. Further detailed analysis showed this explanation helped partially, but did not fully resolve the problem. Yes, some early galaxies do host extremely active supermassive black holes whose radiation significantly boosts their apparent brightness. When astronomers subtracted the estimated black hole contribution from total galaxy luminosity, the most extreme discrepancies narrowed. But even after making those corrections, the early universe still contained roughly twice as many massive galaxies as theoretical predictions permitted. The tension eased somewhat, but did not disappear. The problem remained real and significant. The consistency of this result, across independent surveys, different sky regions, different instruments, and different analysis assumptions, forced cosmologists to reconsider a basic assumption embedded in decades of galaxy formation theory. That assumption concerns the efficiency with which the universe converts available gas into stars. In the modern universe, the one directly observable in our local cosmic neighborhood, star formation is surprisingly and frustratingly inefficient. Most gas inside galaxies never becomes stars at all. It gets heated by radiation from existing stars, stirred by turbulence, blown away by stellar winds, or disrupted by supernova explosions before gravity can collapse it into new stellar objects. A massive molecular cloud containing enough raw material to form millions of stars may spend millions of years producing only a modest number of actual stars before the cloud disperses, its remaining gas scattered and lost, before it can collapse further. Only a small fraction of available gas ever actually ends up locked into stellar interiors. Early galaxies appear to have operated under fundamentally different rules, with dramatically higher star formation efficiency than anything observed in the modern universe. Several explanations have been proposed, none individually sufficient to account for the full discrepancy. One possibility is simply the density of the early universe. In the first billion years after the Big Bang, matter was packed far more tightly together than it is in today's more expanded cosmos. Gas clouds collided more frequently, and those collisions triggered gravitational collapse that converted gas into stars more efficiently. Another idea focuses on the chemical simplicity of early gas. The first stars formed from nearly pure hydrogen and helium gas, without any heavier elements to complicate the thermal processes that govern how gas loses energy and collapses. Under certain conditions, this chemically pristine primordial gas may have collapsed more directly and efficiently than modern gas enriched with carbon, oxygen, and other elements that affect its thermal behavior. Galaxy mergers likely played a crucial role as well. In the early universe, when space was smaller and matter was packed more densely, galaxies were far closer together than they are today. Collisions between galaxies were far more frequent. When galaxies merge, their gas reservoirs get driven toward their centers, compressed to extreme densities that ignite intense bursts of star formation. A galaxy could potentially build much of its total stellar mass in short, violent episodes of merger-driven starburst activity, rather than through slow, steady growth across billions of years. Each of these proposed explanations accounts for part of the observed pattern. None fully resolves it alone. The truth likely involves some combination of all these factors, plus others not yet identified. What is clear is that the early universe assembled structure more efficiently than any model built before Webb predicted. At the centers of many of these surprisingly early galaxies lies a separate and equally troubling mystery. Webb has identified supermassive black holes already in place, already feeding on surrounding matter, already influencing their host galaxies when the universe was less than 500 million years old. Some of these black holes weigh millions of times the mass of our Sunday others, appear to contain billions of solar masses, concentrated into regions smaller than our entire solar system. According to conventional black hole physics, growing a black hole to that mass in that time frame should be flatly impossible. Black holes typically form when massive stars dozens of times more massive than the Sun, exhaust their nuclear fuel and collapse catastrophically. The resulting black hole might weigh tens of solar masses, perhaps reaching up to 100 solar masses in extreme cases. From there, a black hole can grow by consuming surrounding matter, but that growth rate is fundamentally limited by physics. As material falls toward a black hole, it heats up through friction and compression, eventually becoming so hot that it radiates enormous amounts of energy. That outward radiation pressure pushes back against additional material trying to fall inward, creating a natural limit on how fast a black hole can grow. Even under the most favorable imaginable conditions, with unlimited matter available to consume, building a black hole containing 1 billion solar masses through steady accretion should require far longer than 500 million years. The physics simply does not allow it. Yet Webb keeps finding them. This persistent observation has pushed astronomers to seriously consider formation scenarios once considered too speculative to take seriously. Perhaps some black holes formed through the direct collapse of massive primordial gas clouds, bypassing the stellar stage entirely and creating black holes weighing thousands or tens of thousands of solar masses right from the beginning. Perhaps the very first generation of stars, the so-called population 3 stars that formed from chemically pure hydrogen and helium gas, grew thousands of times more massive than any star in the modern universe, then collapsed directly into very large black holes when their short lives ended. Perhaps black hole mergers were far more common in the dense early universe than current models assume, with multiple smaller black holes spiraling together in violent collisions that rapidly built up combined masses large enough to seed the growth of the monsters Webb now observes. None of these ideas has been conclusively confirmed. None can yet be ruled out. The observations demand explanations that push theoretical boundaries into genuinely new territory. What makes this early period so critical is that these rapidly forming galaxies and early black holes shaped absolutely everything that came after in cosmic history. Their intense radiation transformed the universe during an epoch known as reionization, stripping electrons from hydrogen atoms throughout space and making the universe transparent to visible light for the first time. Their supernova explosions enriched intergalactic space with heavy elements, seeding future generations of stars and planetary systems with the chemical ingredients needed to eventually give rise to planets, complex chemistry, and biology. Their gravity pulled surrounding matter into the earliest large-scale structures, the first filaments and cluster seeds that would eventually grow into the vast cosmic web observable across the universe today. If these foundational structures formed earlier and more efficiently than standard models predicted, then the entire timeline of cosmic evolution must shift. Every milestone we thought we understood about when various stages of structure formation occurred needs revision. The universe did not wait patiently for billions of years before becoming complex and organized. It rushed forward, assembling stars, galaxies, and black holes at a pace that genuinely challenges our most carefully developed equations. Which leads to an unavoidable realization. If the universe could build this much sophisticated structure so quickly during its first few 100 million years, then the true scale of what exists today, after 13.8 billion years of additional growth, evolution, and structure formation, may be vastly larger than humanity ever imagined. To begin understanding just how much exists in the cosmos, astronomers periodically conduct what amounts to a census of galaxies. The methodology is conceptually straightforward, even if technically demanding. Point the most capable telescope available at a tiny, seemingly empty patch of sky. Expose the detector for many hours, collecting every photon possible. Count every galaxy visible in the resulting image. Then scale that count upward across the full sphere of observable sky. When the Hubble Space Telescope conducted its deepest observations during the mid-1990s and early 2000s, producing images known as the Hubble Deep Field and later the Hubble Ultra Deep Field, it revealed nearly 10,000 galaxies in a region of sky no larger than a grain of sand held at arm's length. That tiny patch represented roughly 1/113th millionth of the total sky area. From those observations, astronomers carefully estimated that the observable universe contained somewhere between 100 billion and 200 billion galaxies total. The number was almost psychologically impossible to comprehend, yet it felt like a genuine measurement of something fundamental. For years through the 2000s and into the 2010s, that estimate stood as humanity's best answer about how many galaxies share our observable universe. Then Webb turned its gold-coated mirrors toward the same regions of apparent darkness that Hubble had surveyed. Where Hubble saw black gaps between visible galaxies, Webb detected faint infrared glows marking additional galaxies invisible to Hubble's instruments. Where Hubble had captured blurry smudges barely rising above instrumental noise, Webb resolved clear galactic structure. Regions that once appeared empty suddenly revealed themselves as crowded, layered with multiple galaxies at different distances, alive with distant systems that had remained completely hidden from every previous observation. This was not a failure or limitation of Hubble. The Hubble Space Telescope performed magnificently for over 3 decades and delivered discoveries that genuinely reshaped our cosmic perspective. But Hubble was fundamentally constrained by wavelength. It was primarily designed to detect visible light and ultraviolet radiation, the narrow slice of the electromagnetic spectrum that human vision evolved to perceive. As the universe expands, light from distant galaxies gets stretched into longer wavelengths through a process called redshift. By the time light from the most distant galaxies reaches Earth, it no longer exists in the visible range. It has shifted into infrared wavelengths, becoming effectively invisible to Hubble's cameras, but perfectly detectable to Webb's infrared-optimized instruments. The galaxies were always there. Their light was traveling toward Earth, across billions of years. It had simply slipped past our observational capabilities. Existing in wavelengths we lacked the tools to receive. Webb was specifically designed and built to catch it. In one of Webb's most ambitious observing programs, astronomers surveyed a region of sky only slightly larger than 3 full moons placed side by side, a tiny patch representing roughly 1,000th of the total observable sky area. Across hundreds of hours spread over multiple observing sessions, Webb collected more than 10,000 individual exposures, each capturing faint infrared signals that had traveled billions of light years through expanding space. When those thousands of exposures were carefully combined, aligned, and processed to remove noise and artifacts while preserving genuine galactic signals, the result was genuinely staggering. Nearly 800,000 distinct galaxies filled the frame. 800,000 separate galaxies in a patch of sky most people would glance at and dismiss as empty darkness. To appreciate the scale of that result, consider this. If you were to print Hubble's famous ultra-deep field image on a standard sheet of paper, displaying Webb's equivalent deep field image at the same scale and detail would require a print more than 13 feet tall and 13 feet wide, a wall-sized mural of cosmic history where every single point of light is not a star, but an entire galaxy, each containing anywhere from millions to trillions of individual stars. This single result forced a fundamental revision in the cosmic census. The 200 billion galaxy estimate that had stood for years was not just slightly wrong, it was catastrophically underestimated. By counting galaxies in deep infrared surveys and scaling across the full observable sky, Astronomers now estimate the observable universe contains somewhere between 2 trillion and 3 trillion galaxies, roughly 10 to 20 times more than Hubble had suggested. And the observable universe, as vast as it is, represents only a fraction of what physically exists. To fully understand what this means, it helps to understand what we actually mean when we say observable universe, and why that boundary exists, not because of technological limitations, but because of the fundamental physics of space and time. Everything you perceive, everything you see, hear, and experience is not a real-time feed of the present moment. It is a record of the recent past, delayed by the time it takes information to travel from its source to your senses. This is not philosophical abstraction. It is the inevitable consequence of a simple physical fact. Information cannot travel instantaneously. Light, electromagnetic radiation, every signal carrying information from one point to another moves at a finite speed. That speed is approximately 186,000 miles every second, fast enough to circle the entire Earth more than 7 times between one heartbeat and the next. Nothing in the universe moves faster. Nothing can. This represents an absolute speed limit built into the structure of reality itself. Yet even at that incomprehensible velocity, distance transforms instantly into delay. The farther light must travel to reach your eyes, the older the image it carries when it finally arrives. Consider what this means at even modest distances. When you see a building 1 mile away, you are actually observing it as it existed roughly 5 millionths of a second ago. The light reflecting off that structure took that tiny fraction of time to cross the intervening space. The delay is infinitesimally small and makes no practical difference, but the principle is absolute. When you look at the moon hanging in the night sky, you see it not as it exists in your present moment, but as it appeared 1.3 seconds ago. That is how long it takes light to cross the 240,000 miles separating Earth from its natural satellite. If the moon were somehow to vanish in an instant, you would continue seeing it peacefully in the sky for another second and a third before the information about its disappearance could possibly reach you. The sun, sitting at the center of our solar system 93 million miles away, appears to us as it existed 8 minutes and 20 seconds in the past. Every sunrise you have ever witnessed, every sunset, every moment spent in sunlight, happened 8 minutes after the light carrying that warmth left the sun's surface. We have never seen the sun as it is. We see it as it was, watching a perpetually delayed broadcast. The night sky is not a live feed of the cosmos. It is an archive of information, a layered museum of light carrying messages from countless different moments in time. Every star visible to the naked eye exists within our own Milky Way galaxy. Even these relatively nearby neighbors appear as they existed years, decades, or centuries in the past. Proxima Centauri, the nearest star beyond our sun, sits 4.2 light-years away. When you see its faint light, you are observing it as it appeared 4.2 years ago. The light you detect tonight left that star's surface, while entire seasons cycled through on Earth, while your life changed in countless ways. The center of our Milky Way galaxy, that dense core where hundreds of billions of stars orbit a supermassive black hole, exists 26,000 light-years from Earth. Every image we capture of the galactic center shows it as it appeared 26,000 years ago. When those photons began their journey, humans were still living in the Stone Age. The entire span of recorded human civilization, every empire that rose and fell, every scientific achievement, every technological development, occurred while those photons traveled silently through space. As observations extend beyond the Milky Way into the incomprehensible spaces between galaxies, we stop observing anything resembling the present. The Andromeda Galaxy, our nearest large galactic neighbor, appears to us as it existed 2.5 million years ago. Other galaxies in our local group show themselves as they were tens of millions of years in the past. The night sky transforms from a display of distant lights into something far more profound, a temporal archive where every point of light represents a different moment in cosmic history. Closer objects appear nearly contemporary. More distant objects reveal progressively older versions of reality. Every photon becomes a time capsule, a messenger carrying information about when and where it originated, preserved during its journey across the universe. As photons travel through expanding space, something fundamental happens to them. The expansion of space stretches the light itself. Imagine a wave traveling across the surface of an ocean with a wavelength determined by the distance between successive crests. Now imagine that ocean suddenly growing larger, with every point on its surface moving away from every other point. As the ocean expands, the wave gets stretched along with it. The distance between crests increases. The wavelength grows longer. Light behaves exactly the same way as it travels through expanding space. When a photon is created, it carries a specific wavelength determined by the physical process that generated it. High-energy photons have short wavelengths appearing blue or ultraviolet. Lower-energy photons have longer wavelengths appearing red or infrared. But as space expands during the photon's journey, the wavelength gets stretched. Energetic blue light gradually shifts toward red. Ultraviolet light moves into the visible spectrum, then continues shifting into infrared, and eventually into radio wavelengths. This phenomenon, called redshift, is not merely a cosmetic change in color. It is a precise record of cosmic expansion, a measurement of how much the universe has grown since the photon began its journey. The more stretched the light, the longer it has been traveling, and the earlier in universal history it must have been emitted. Redshift acts as a cosmic timestamp, allowing astronomers to determine not just how far away an object is, but when, in the history of the universe, it existed. The most distant objects in the sky do not just appear far away. They appear ancient, their light stretched by billions of years of cosmic expansion, carrying information about an era when the universe was fundamentally different. For most of the 20th century, astronomers relied on telescopes optimized to detect visible light and ultraviolet radiation, the narrow slice of the electromagnetic spectrum human vision evolved to perceive. These instruments, culminating in the Hubble Space Telescope, revolutionized our understanding of galaxies, star-forming regions, and the large-scale architecture of cosmic structure. But as scientists attempted to peer farther back in time, to observe the universe during its earliest epochs, something frustrating kept happening. The universe seemed to fade away, not because nothing existed in those ancient eras, but because the light from those distant objects had been stretched so dramatically by billions of years of cosmic expansion that it no longer appeared in wavelengths Hubble could detect. Those ancient galaxies did not disappear. Their light simply drifted beyond the range of visible and ultraviolet observation, slipping into the infrared portion of the spectrum where Hubble's instruments struggled to function. It was as if humanity had been trying to listen to a conversation happening in a frequency our ears could not detect. The information existed, traveling through space toward us, but we lacked the proper instruments to receive it. The James Webb Space Telescope was specifically designed and engineered to solve this problem. Webb's primary mirror spans more than 21 feet in diameter, constructed from 18 hexagonal segments, each coated with a microscopically thin layer of gold, precisely 99 nanometers thick. Gold was chosen for a specific physical reason. It reflects infrared light with exceptional efficiency, far better than the aluminum coating used on most optical telescopes. Webb does not orbit Earth as Hubble does. Instead, it operates at a gravitationally stable location known as the second Lagrange point, nearly 1 million miles from Earth, roughly 4 times farther than the Moon. This remote position offers crucial advantages. Webb sits in permanent shadow, shielded from the heat and light of the Sun, Earth, and Moon by a sunshield the size of a tennis court, consisting of 5 layers of specially engineered material. That thermal isolation is absolutely essential, because Webb is an infrared telescope, and infrared radiation is intimately linked to heat. Everything warm emits infrared light. A telescope operating at room temperature would generate so much infrared radiation from its own structure that it would completely overwhelm the faint signals from distant galaxies. To detect ancient light that has been traveling for billions of years, Webb must itself become extraordinarily cold. Webb's instruments are cooled to approximately 370 degrees below 0 Fahrenheit, barely above absolute zero, the coldest temperature physically possible. At these extreme temperatures, the telescope itself generates almost no infrared radiation. Only at this level of thermal isolation can Webb become sensitive enough to detect the faintest whispers of ancient light, photons that have been traveling, stretched, and diluted by their journey across almost the entire observable universe. When Webb stares at a patch of sky that appears utterly black to human eyes, to Hubble, to every ground-based telescope ever built, it is not searching for emptiness. It is waiting with mechanical patience, collecting photons one by one as they arrive after journeys lasting billions of years. Webb might observe the same tiny region of sky for dozens of hours, even multiple days, patiently gathering every photon it can detect, building up an image from light so faint that each individual photon matters. And what Webb finds in that apparent darkness is not a tentative, primitive cosmos just beginning to organize itself. It finds a universe that is already surprisingly mature, already busy with activity, already filled with structure. Some of the galaxies Webb has detected formed when the universe was merely 300 million years old, less than 3% of its current age of 13.8 billion years. To put this in perspective, imagine compressing the entire history of the universe into a single calendar year. The Big Bang occurs at the very first moment of January 1st. Those incredibly early galaxies would appear on January 2nd, just one day after the universe itself began. According to the cosmological models that astronomers spent decades developing and refining, this epoch, often called cosmic dawn, should have been a relatively dim and quiet period. The universe had just emerged from what is known as the cosmic dark ages, a period when space was filled with neutral hydrogen gas that blocked almost all light. The very first stars were expected to ignite slowly and tentatively. Early galaxies were predicted to be small, fragile collections of gas and newborn stars, requiring hundreds of millions of additional years to accumulate enough matter to become bright and substantial. But Webb saw something completely different. It discovered galaxies that were already bright, already massive, already forming stars at intense rates that rival or exceed the star formation activity in much later galaxies. Some were luminous enough that even if they were significantly more distant than initial measurements suggested, Webb could still detect them easily. That brightness carries profound implications. Bright galaxies require vast populations of stars, and stars do far more than simply shine. Inside their cores, nuclear fusion forges heavier elements that did not exist in the universe's earliest moments. The Big Bang produced primarily hydrogen and helium, with trace amounts of lithium. Everything heavier, every atom of carbon, oxygen, nitrogen, iron, silicon, calcium, and all the other elements that make up planets and living things, must be created inside stars through fusion. Those heavier elements only escape into space when stars die, either through stellar winds during their lifetimes or through explosive supernova events at the end of their existence. When Webb detects significant quantities of heavy elements in galaxies that formed just a few 100 million years after the Big Bang, it is seeing irrefutable evidence that earlier generations of stars had already completed their entire life cycles. Stars had formed, lived their lives, and died, enriching the interstellar medium with heavy elements, all within the universe's first few 100 million years. The cosmic clock was not just running on schedule, it was running ahead of schedule, accelerating through stages of complexity that were supposed to take far longer. The universe did not ease gradually into complexity through patient processes unfolding over vast spans of time. It rushed toward organization and structure with surprising urgency that our models had not anticipated and still struggle to fully explain. There is something genuinely profound about the nature of these observations. Webb does not capture these images instantaneously like a camera photographing something in the same room. It gathers photons that have been traveling for more than 13 billion years, particles of light that began their journey when the universe was young, unfamiliar, and radically different from the cosmos we inhabit today. When that ancient light first started moving through space, Earth did not exist. The sun had not formed. The Milky Way was still slowly assembling itself from clouds of gas and dark matter that would require billions of additional years to coalesce into a mature galaxy. There were no planets, no oceans, no chemistry complex enough to support biology, no observers to witness those distant galaxies in their youth. Every chapter of Earth's history, from its formation through its entire geological timeline, every species that has ever lived, every civilization that has ever existed, the entire span of human experience from prehistoric times to the present moment, all of it unfolded while those photons were already traveling through space, carrying their ancient message forward through time. By the time Webb finally detects them, we are not witnessing current events. We are not seeing these galaxies as they exist today. We are witnessing moments that happened once, impossibly long ago, preserved perfectly in transit, like messages cast across a vast ocean of space and time. This is why astronomers say the James Webb Space Telescope does not simply look far away into distant regions of space. It looks backward through time itself. Distance and time become inseparable concepts. Nearby objects reveal the universe closer to the present. More distant objects show progressively earlier stages of cosmic history, like turning back the pages of a book until you reach chapters written billions of years ago. Yet, even Webb's extraordinary capabilities cannot overcome a fundamental limit imposed by physics itself. No telescope, regardless of how powerful humanity might eventually build it, can see beyond a boundary determined by the nature of cosmic expansion and the finite age of the universe. That boundary is called the edge of the observable universe, and it exists not because of any technological shortcoming, but because of how space expands and how long the universe has existed. The observable universe is a vast sphere centered on Earth, with a radius of approximately 46.5 billion light-years in every direction. This number might seem surprising. If the universe is only 13.8 billion years old, how can we observe objects 46.5 billion light-years away? The answer lies in cosmic expansion. Space itself has been expanding continuously since the Big Bang. The galaxies Webb observes at the greatest distances were much closer when their light first began its journey. But as that light traveled toward us, the expansion of space carried those galaxies farther away. By the time their ancient light finally reaches Webb, after a journey lasting over 13 billion years, the sources of that light now lie billions of light years farther away than when the photons originally departed. The observable universe is therefore larger than 13.8 billion light years in radius, because space expanded during the photon's transit. Webb is now pushing observations closer to that absolute boundary than any previous instrument, detecting galaxies at distances that were once thought completely unreachable, revealing structure in epochs so ancient that light from those eras has been traveling for nearly the entire history of the cosmos. But even Webb, with all its technological sophistication, cannot observe beyond the cosmic horizon. And this is where our understanding of reality becomes genuinely unsettling. Space does not stop at the edge of what we can observe. The universe does not end at the cosmic horizon. Beyond that observational boundary, galaxies continue to exist. Stars continue to ignite and burn through their fuel. Black holes continue to form and merge. Planets continue to orbit their host stars. Entire cosmic histories continue to unfold in regions that are forever hidden from us. Not because our technology is inadequate, not because we lack sufficiently powerful telescopes, but because the fundamental structure of space-time itself prevents information from those regions from ever reaching us. The universe beyond our observable horizon is not just currently unreachable, it is permanently and fundamentally beyond any possible observation, regardless of how advanced our instruments might someday become. Why? Because those distant regions of space are receding from us faster than light can travel. The expansion of space itself is not limited by the speed of light, the way that moving objects are. Space can expand faster than light travels. In regions sufficiently distant from us, the cumulative expansion rate means that any light emitted there today will never reach us. Those photons will spend eternity traveling in our direction, but will never close the gap, because the space between us keeps growing faster than light can traverse it. The light from those regions is not delayed. It is permanently inaccessible. Those regions of the universe are not in our future observational reach. They are outside it forever. This means that when we speak of the observable universe, we are not simply describing the current limit of our telescopes. We are describing a permanent physical horizon determined by the age of the universe and the rate at which space expands. The observable universe, vast beyond comprehension, is only a bubble within a far larger reality that we can never access regardless of our technological future. And here's where the full weight of Webb's discoveries begins to settle in. Within that bubble alone, Webb has found roughly 2 trillion to 3 trillion galaxies, 2 trillion to 3 trillion separate island universes, each containing billions to hundreds of billions of stars, each potentially hosting billions of planets, each representing a complete ecosystem of cosmic processes extending across billions of years. That is within the observable portion of the universe, the small fraction of reality we can physically access. If the processes Webb has observed, the surprising efficiency of early galaxy formation, the rapid assembly of massive structures, the abundance of cosmic organization, and what were supposed to be empty or primitive eras, apply throughout the universe as a whole, then the true number of galaxies in all of existence could be vastly larger than even those already staggering estimates. We do not know how large the universe beyond our horizon is. It could be finite, eventually curving back on itself at some enormous scale we cannot measure. It could be effectively infinite, extending without boundary in every direction. Current evidence does not allow us to distinguish between these possibilities. But even if we conservatively assume the full universe is only modestly larger than the observable portion, the implied number of galaxies, stars, and planets becomes incomprehensibly large. Some cosmological models, particularly those derived from inflationary theory, suggest the full universe may be vastly larger than the observable portion, potentially by factors that make the word large seem inadequate. In the most expansive inflationary scenarios, the observable universe, despite containing 2 trillion to 3 trillion galaxies and extending 46.5 billion light-years in every direction, represents such a small fraction of the full universe that comparing the two requires notation that strains description. The true universe might contain more galaxies than there are atoms in the observable universe. These are not fringe speculations. They are predictions of theoretical frameworks developed to explain the uniformity and structure we observe in the cosmic microwave background, the faint afterglow of the Big Bang itself. They are not confirmed. They cannot yet be tested, but they represent the direction that serious theoretical work points when the full implications of cosmic expansion, cosmic age, and the structure Webb observes are taken together. What Webb has done, perhaps more than any previous scientific instrument, is bridge the distance between our theoretical understanding of the universe and the observational reality we actually inhabit. It has shown us that the universe formed complex structure faster than we expected. It has shown us that the observable cosmos is far more densely populated than we realized. It has revealed that even within the portion of the universe we can see, there is far more matter, far more energy, far more history, and far more ongoing complexity than our pre-Webb models had captured. And it has clarified, perhaps more sharply than anything before it, how much of the universe lies permanently, fundamentally, forever, beyond any possible observation. The questions Webb's discoveries have generated are now driving the next generation of observational and theoretical work. How did the first stars actually form? What physical conditions allowed the first generation of objects to assemble so rapidly? Were the formation pathways of population 3 stars, those first chemically pure stars that must have preceded every subsequent generation, fundamentally different from the formation of stars in the modern universe? How did supermassive black holes grow to billions of solar masses within the universe's first 500 million years? What seeded their formation? And what physical processes allowed them to bypass the apparent growth rate limits that standard black hole physics predicts? Astronomers are currently developing more sophisticated models of early galaxy formation, incorporating higher star formation efficiencies, different treatments of the gas physics in metal-poor environments, and more detailed modeling of how dark matter halos grew and merged in the dense early universe. Future observations with Webb itself, combined with data from next-generation facilities and from gravitational wave observatories capable of detecting signals from early black hole mergers, will help test these models against the reality Webb is now revealing. The cosmic microwave background, that faint thermal afterglow of the Big Bang preserved across the entire sky, holds additional information about the conditions that prevailed in the universe's earliest moments. Future missions designed to map the polarization patterns of this ancient radiation with unprecedented precision will reveal details about inflation, about the primordial fluctuations that seeded all subsequent structure, and potentially about the physical processes that allowed structure to form as rapidly as Webb has shown it did. What remains perhaps most remarkable about this moment in astronomical history is how much Webb has managed to challenge in such a short operational time. The telescope became scientifically operational in mid-2022, and within its first few years of operation, it had already generated enough observations to force revisions in fundamental aspects of cosmological theory. The too much too soon problem, the unexpectedly rapid growth of supermassive black holes, the extraordinary density of early galaxy populations, the sheer number of galaxies filling the observable universe. These are not small discrepancies at the edge of statistical significance. They are substantial, consistent, repeatedly verified departures from what our best pre-Webb models predicted. Science progresses precisely through this process. Careful observations reveal discrepancies between prediction and reality. Those discrepancies drive theorists to identify what assumptions in existing models must be revised or abandoned. New models make new predictions that observational tests can evaluate. The cycle continues, with each iteration bringing our understanding closer to a more complete and accurate description of how the universe actually works. Webb has not broken physics. It has revealed that some of the assumptions embedded in our physics needed testing. And now that testing is underway, the universe Webb is revealing is older in its complexity, larger in its population of galaxies, richer in its early chemical evolution, and more surprising in its early black hole growth than any model built before Webb predicted. Those surprises are not cause for concern. They are cause for exactly the kind of scientific excitement that drives the development of new understanding. Every discrepancy Webb identifies is a window into physics that was previously hidden, a constraint on the range of models that can possibly describe our universe, and an invitation to think more carefully about the processes that shaped everything we observe. Within the observable universe, an object roughly 46.5 billion light-years in radius, the number of galaxies Webb has now revealed is closer to 2 trillion than to the 200 billion estimate that stood before its launch. Each of those 2 trillion galaxies is a system of stars, gas, dust, dark matter, and chemistry, processing matter and energy on timescales of billions of years, potentially hosting planets with conditions capable of supporting chemistry far more complex than anything in the interstellar medium. The scale of this is simply beyond the reach of human intuition. We have no biological capacity to truly grasp 2 trillion of anything. We can write the number, we can compute with it, we cannot feel it in any meaningful sense. What we can do is follow the evidence wherever it leads, build instruments capable of accessing portions of the electromagnetic spectrum previously unexplored, and allow the universe itself to reveal its structure, rather than assuming our initial models were complete. Webb is doing exactly that. And what it is finding, observation by observation, survey by survey, is a cosmos far richer, far more active in its early history, and far more surprising in its organizational capacity than the careful theoretical work of previous generations had managed to anticipate. The early universe did not slowly, tentatively, feel its way toward complexity. It assembled structure with an urgency and efficiency that our equations are still working to explain. The observable universe is not sparsely populated with a few 100 billion isolated galactic islands. It is teeming, layered with galaxies at every scale, filled with activity at every epoch Webb can now reach. And beyond the boundary of what any telescope can ever observe, reality continues in ways and at scales we may never directly measure. The scientific community has generations of work ahead to build theories adequate to explain what Webb is finding. The observational data will continue to accumulate, the models will continue to evolve, and the universe, patient and indifferent, will continue to reveal its structure to any instrument sensitive enough to detect the ancient light still arriving from its earliest epochs, carrying encoded within each photon the story of how complexity first emerged from primordial simplicity, faster and more abundantly than anyone who built those first models ever imagined possible. To truly appreciate the magnitude of what Webb has accomplished, it helps to understand the decades of technological development and scientific struggle that preceded it. Astronomy has always been fundamentally a science of light, but light is not a single thing. It is a spectrum, a continuous range of electromagnetic radiation spanning wavelengths from gamma rays and X-rays at one extreme, through ultraviolet, visible light, infrared, and microwave radiation to radio waves at the other. Human eyes evolved to detect only a narrow slice of this spectrum, the range of wavelengths most abundantly produced by our sun, and scattered or reflected by the surfaces and atmospheres of terrestrial objects. But the universe produces radiation across the entire electromagnetic spectrum, and different physical processes produce different kinds of radiation. A complete picture of the universe requires instruments sensitive to each portion of the spectrum. Ground-based astronomy was limited from its beginning by Earth's atmosphere. The atmosphere absorbs or scatters most non-visible radiation, acting as a kind of optical filter that blocks precisely the wavelengths astronomers most needed to observe to study the distant universe. Radio waves pass through the atmosphere reasonably well, which is why radio astronomy flourished after the mid-20th century and produced discoveries including pulsars, quasars, and the first maps of cosmic large-scale structure. But infrared radiation, the wavelengths Webb was designed to detect, is almost entirely absorbed by water vapor and carbon dioxide in Earth's atmosphere before it reaches the ground. This meant that for most of the 20th century, the most ancient and distant galaxies in the universe were simply invisible to astronomers. The light existed. It was arriving at Earth from distances of billions of light years, but it was being absorbed in the atmosphere before any ground-based instrument could detect it. Placing a telescope above the atmosphere was the only solution, and the cost and complexity of doing so meant that infrared space astronomy was a long time coming. Several important infrared space observatories preceded Webb, including the Spitzer Space Telescope, which operated from 2003 to 2020, and provided the first detailed infrared surveys of nearby and moderately distant galaxies. But Spitzer's mirror was only 1.4 meters in diameter, giving it sensitivity roughly 100 times lower than Webb. It could reveal infrared emission from nearby objects and moderately distant galaxies, but lacked the collecting area to detect the faintest ancient light from the universe's earliest epochs. Webb represents a qualitative jump forward in infrared observational capability. Its 6.5-meter primary mirror collects more than 20 times the light of Spitzer's mirror. Its position at the second Lagrange point, combined with its multi-layered sunshield, allows it to operate at temperatures cold enough to detect thermal infrared emission that Spitzer, orbiting closer to the warm sun, could not reach. And its instruments incorporate detector technologies developed over decades of laboratory work, specifically to push sensitivity to new limits. The result is a telescope that can detect infrared light from objects so distant, so ancient, and so faint that detecting them with any previous instrument was physically impossible. The choice to prioritize infrared observation was not arbitrary. It followed directly from a theoretical understanding of how cosmological redshift affects the light of distant galaxies. When the universe was young and galaxies were forming their first generations of stars, those stars emitted light across a wide range of wavelengths, including a great deal of ultraviolet radiation from the hot, massive, short-lived stars that dominate young stellar populations. But as the universe has expanded over 13.8 billion years, all that ultraviolet light has been stretched into progressively longer wavelengths. By the time it reaches Earth from galaxies that existed only a few 100 million years after the Big Bang, it has been redshifted from ultraviolet through visible wavelengths and deep into the infrared. Webb was designed to detect exactly this kind of light, ancient ultraviolet radiation transformed by cosmic expansion into infrared wavelengths accessible to Webb's gold-coated mirror and cooled infrared detectors. Understanding redshift in more detail reveals just how powerful a tool it is for cosmic archaeology. The amount of redshift in a galaxy's light is directly related to how much the universe has expanded since that light was emitted. Astronomers quantify this using a number called the redshift parameter, conventionally written as the letter Z. A galaxy with a redshift of 0 is effectively at the same cosmic epoch as Earth, meaning its light has not been significantly stretched. A galaxy with a redshift of 1 has its light wavelengths doubled, meaning the universe has expanded by a factor of 2 since that light was emitted. A galaxy with a redshift of 10 has its light wavelengths stretched by a factor of 11, corresponding to a time when the universe was only about 500 million years old. When Webb observes objects with redshifts of 10, 12, 15 or higher, it is detecting light emitted when the universe was a tiny fraction of its current age. Some of Webb's early survey observations identified candidate galaxies with redshifts approaching or potentially exceeding 20, corresponding to epochs when the universe was only 100 to 200 million years old. These observations pushed the boundaries of what had previously been considered detectable, let alone achievable with practical observing times. The concept of look-back time gives another way to understand what these observations represent. Look-back time is simply the amount of time it took light from a distant object to reach us, which is equivalent to how long ago in the past that object existed when it emitted the light we now detect. For objects at a redshift of 10, the look-back time is approximately 13.2 billion years, meaning we are observing those objects as they existed 13.2 billion years ago, when the universe was only about 600 million years old. For objects at redshift 15 or higher, the look-back time approaches 13.5 billion years, reaching into the universe's first few 100 million years, when the very first stars were igniting, and the first galaxy-scale structures were beginning to assemble. The depth of cosmic time these numbers represent is genuinely staggering. 13.5 billion years ago, our sun did not exist. The atoms now comprising every human body on Earth were distributed across interstellar space in clouds of gas that would not collapse into a protostellar disk and begin forming our solar system until roughly 9 billion years later. The geological record of Earth extends back only about 4 billion years. Human civilization has existed for perhaps 10,000 years, and yet the light Webb collects from the most distant objects it observes began its journey 13,500 million years ago, before any of the structures we consider familiar or permanent had formed. The sheer scale of cosmic time is one of the most counterintuitive aspects of modern astronomy. Human psychology evolved to deal with timescales of days, seasons, lifetimes, and at most generations. The history of human civilization, roughly 10,000 years, feels vast compared to an individual human life. The history of Earth, 4 billion years, is 100,000 times longer than all of recorded human civilization combined. But the history of the universe, 13.8 billion years, is more than 3 times longer than Earth's entire geological history. And the objects Webb observes, at the highest redshifts, existed before Earth itself had any of the raw materials from which it would eventually form. Placing Webb's discoveries in this temporal context makes the too much too soon problem even more striking. The galaxies Webb has found at redshifts of 10 and above existed when the universe was less than 6% of its current age. The most extreme early galaxies, those forming just 200 to 300 million years after the Big Bang, existed when the universe was between 1.5 and 2% of its current age. Finding complex, chemically mature, highly luminous galaxies at those epochs is roughly equivalent to finding a fully modern city, complete with skyscrapers, power grids, and complex infrastructure on Earth during the Hadean Eon, before the planet's crust had even fully solidified. The analogy is imprecise, but it captures the sense in which the observed complexity seems to have appeared far earlier than the underlying processes should have allowed. The theoretical framework astronomers use to describe galaxy formation is called lambda CDM, where lambda refers to the cosmological constant that drives the accelerating expansion of the universe, and CDM stands for cold dark matter. This framework describes how dark matter halos form, how ordinary baryonic matter falls into those halos, how gas cools and condenses, and how stars and galaxies form from that condensed gas. Lambda CDM has been extraordinarily successful. It correctly predicts the large-scale distribution of galaxies across the modern universe, the temperature fluctuations in the cosmic microwave background, the abundance of galaxy clusters, and many other observational properties of the cosmos. It is one of the most thoroughly tested theoretical frameworks in all of science. But Webb's observations of the early universe reveal tension with lambda CDM's predictions about how galaxies should have formed in the universe's first billion years. The framework does not flatly fail. It correctly predicts that galaxies should exist at those early epochs, and Webb has confirmed their existence. The problem is quantitative. Lambda CDM predicts how many galaxies of a given mass should exist at a given redshift. And at high redshifts, Webb consistently finds more massive galaxies than the model predicts, often by factors of several to 10. The discrepancy is not explained by observational errors. It appears to be a genuine limitation of the model's description of early star formation efficiency. Several theoretical modifications have been proposed to bring lambda CDM into better agreement with Webb's observations. One approach involves modifying the treatment of feedback processes in early galaxies. In the modern universe, stellar feedback, including radiation pressure from hot stars, stellar winds, and supernova explosions, is one of the primary mechanisms that limits star formation efficiency by heating and dispersing gas. Current models may overestimate how effectively these feedback processes worked in the early universe, where conditions were different. If early feedback was less efficient at suppressing star formation than current models assume, galaxies could have converted their gas into stars more rapidly, producing the larger stellar masses Webb observes. Another approach focuses on the nature of dark matter itself. The standard cold dark matter model describes dark matter as particles moving slowly compared to the speed of light in the early universe. Alternative models, including warm dark matter, where dark matter particles move faster, or fuzzy dark matter, where dark matter behaves quantum mechanically on galactic scales, predict different distributions of dark matter halo masses at early times. If dark matter halos assembled differently than the standard model predicts, the formation of early galaxies would have proceeded along different pathways, potentially producing the larger and more numerous early galaxies Webb has detected. A more radical possibility is that the standard cosmological model needs revision not just in its treatment of galaxy formation processes, but in some of its fundamental assumptions about the nature of dark energy or even the laws of gravity. Some researchers have proposed modifications to general relativity on cosmological scales that could change how structure forms. Others have explored alternatives to the cosmological constant as a description of dark energy that would produce different expansion histories and different rates of structure formation. These ideas remain speculative and lack the observational support of lambda CDM, but the tension between Webb's observations and standard model predictions keeps them in active scientific discussion. The question of what the first stars were actually like is central to understanding everything Webb has observed about early galaxy evolution. Astronomers call these hypothetical first stars population 3 stars, designating them with a Roman numeral to distinguish them from the later stellar generations that formed from gas already enriched with heavy elements by prior stellar generations. Population 3 stars have never been directly observed. They existed so early in cosmic history and were so short-lived that no individual Population 3 star can be detected by Webb or any other current instrument. But their existence is theoretically certain. The universe contained hydrogen and helium after the Big Bang. Those elements had to form the first stars. And those first stars must have been fundamentally different from any star that has existed since. Because primordial gas contained only hydrogen and helium, without any heavier elements to act as cooling agents, the minimum mass required for a collapsing gas cloud to ignite nuclear fusion was much higher than in modern star-forming regions. Current theoretical calculations suggest that Population 3 stars were extraordinarily massive, potentially ranging from tens to thousands of times the mass of our Sunday. Some theoretical models suggest the most massive Population 3 stars may have exceeded 10,000 solar masses, making them far larger than the most massive stars known in the present universe, which top out at around 300 solar masses. These extraordinarily massive first stars would have burned through their nuclear fuel extremely quickly, living for only a few million years before ending their lives in catastrophic explosions or direct collapses to black holes. Their deaths would have been among the most violent events in the universe's history, producing explosions far more energetic than ordinary core collapse supernovae. These explosions, known as hypernovae or pair-instability supernovae, depending on the precise mass and mechanism, would have scattered enormous quantities of heavy elements into the surrounding gas, seeding it with the first oxygen, carbon, silicon, and other elements that would make all subsequent star formation chemically richer. The transition from Population 3 stars to the next generation of star formation, called Population 2 stars, represents one of the most important phase transitions in cosmic history. Once enough heavy elements existed in the interstellar medium to act as cooling agents, the gas could collapse more efficiently and produce stars of a much wider range of masses, including many low-mass stars similar to our Sun that survive for billions of years. The presence of heavy elements detected by Webb in galaxies just a few 100 million years after the Big Bang tells us that this transition from Population 3 to Population 2 star formation happened very rapidly, perhaps within the universe's first 200 to 300 million years. Direct detection of Population 3 stars, or of galaxies dominated by Population 3 stellar populations, remains one of the most important scientific goals for Webb and future telescopes. Some theoretical models predict that individual Population 3 stars would be too faint to detect at cosmological distances, but galaxies hosting large populations of Population 3 stars might be detectable through specific spectral signatures, particularly strong emission from hydrogen and helium, combined with a complete absence of emission from heavier elements like oxygen and carbon. Webb is actively searching for these signatures. Any confirmed detection of a genuine Population 3 galaxy would be one of the most significant astronomical discoveries in history, providing a direct observational window into the universe's first stars and the very beginning of cosmic chemical enrichment. The story of heavy element production and dispersal connects directly to one of the most profound and philosophically resonant aspects of modern astrophysics. Every atom of every element, heavier than hydrogen and helium, that exists anywhere in the observable universe, was forged inside a star. The carbon in every organic molecule, the oxygen in every breath of air, the iron in every red blood cell, the calcium in every bone, the silicon in every grain of sand. None of these elements existed in the universe's first few minutes. They are all products of stellar nucleosynthesis, the nuclear fusion reactions that power stars across their lifetimes, and of the spectacular explosions that end the lives of massive stars. When a massive star exhausts its fuel and explodes as a supernova, it sprays these heavy elements outward at velocities of tens of thousands of kilometers per second, enriching the surrounding interstellar medium with chemical complexity that was not there before. That enriched gas mixes with primordial hydrogen and helium, forming the raw material from which the next generation of stars and their planetary systems will form. Our Sun formed from gas, enriched by many previous generations of stellar birth and death. The atoms in your body have been through stellar interiors and supernova explosions multiple times over the course of the universe's history. This cycle of stellar birth, nuclear synthesis, death, and chemical enrichment is what astronomers call stellar evolution on galactic scales, and it is one of the primary processes Webb is now tracing back to its earliest manifestation. The rapid appearance of heavy elements in early galaxies, detected through Webb's spectroscopic observations, tells us that this cycle had already completed multiple full iterations before the universe was even 500 million years old. Stars formed, burned, and died multiple times over, each generation chemically enriching the interstellar medium that the next generation would form from. The implications extend beyond chemistry. The process of chemical enrichment is directly connected to the formation of planets, and ultimately to the conditions necessary for biology. Planets form from the dust and gas in the disk of material surrounding a newly forming star. Rocky planets, the kind that might support liquid water and complex chemistry, require significant quantities of silicon, iron, magnesium, and oxygen. If the first generations of stars enriched the interstellar medium with these elements rapidly, then the conditions necessary for rocky planet formation appeared much earlier in cosmic history than previously thought. This means the potential timeline for the emergence of planetary systems capable of supporting complex chemistry extends much further back toward the universe's beginning than pre-Webb models suggested. Astronomers have long speculated about whether complex chemistry and biology might have arisen elsewhere in the universe, and if so, when the conditions for it first became available. Webb's observations suggest that chemically enriched environments suitable for rocky planet formation appeared in some galaxies within the universe's first billion years. The first planetary systems to host liquid water, complex organic chemistry, and potentially prebiotic conditions might have formed much earlier than any estimate made before Webb began observing. This does not mean that life necessarily arose early. The origin of life remains deeply mysterious, and the mere availability of the necessary raw materials does not guarantee the emergence of biology, but it pushes the window of cosmic opportunity for life substantially further back in time. Returning to the scale of the observable universe, the 2 trillion to 3 trillion galaxies Webb surveys suggest exist within our cosmic bubble. Each tell their own story of stellar birth, chemical evolution, planetary formation, and the complex interplay of dark matter, ordinary matter, and radiation that shaped all structure in the universe. Each of those galaxies has its own history of mergers, interactions, periods of intense star formation, and periods of quiescence. Each has its own population of black holes, ranging from the stellar mass black holes left behind when individual massive stars die, to the supermassive black holes that sit at the centers of nearly every large galaxy, and whose masses range from millions to billions of solar masses. The total number of stars in the observable universe, calculated by multiplying the estimated number of galaxies by the estimated average number of stars per galaxy, reaches numbers that language struggles to describe. Current estimates place the total number of stars in the observable universe at around 100 sextillion to 1 septillion, written as numbers that look like 1, followed by 23 or 24 zeros. Every one of those stars is a self-gravitating nuclear fusion reactor, converting hydrogen into helium and heavier elements through processes that release energy at rates dwarfing anything achievable in human technology. Most of those stars are orbited by planetary systems. Many of those planetary systems include rocky planets in temperature ranges where liquid water could potentially exist. The observable universe is, as far as current knowledge extends, extraordinarily well populated with the structures and conditions that enable complexity. The transition from this observed richness within the observable universe to what might exist beyond its boundaries involves a conceptual leap that is genuinely difficult to make. We have direct evidence, from Webb surveys and from a century of observational astronomy, about what the observable universe contains. We have zero direct evidence about what lies beyond the cosmic horizon, but we have theoretical frameworks tested and refined against observations of the observable universe that make predictions about the structure and extent of the full universe, including its unobservable regions. The inflationary model of the early universe, originally proposed in 1980 by Alan Guth and subsequently developed and refined by many physicists, was designed to explain several otherwise puzzling features of the observable universe. Why is the cosmic microwave background so remarkably uniform in temperature across regions of the sky that were never in causal contact with each other before the light we observe was emitted? Why does the geometry of space appear flat to extremely high precision, despite the fact that a wide range of values for cosmic curvature are theoretically possible? Why do we not observe certain exotic relics, like magnetic monopoles, that should have formed abundantly in a universe without inflation? Inflation answers all of these questions by proposing that the universe underwent a brief but extraordinarily rapid period of exponential expansion in its first tiny fraction of a second. During this inflationary period, the universe expanded by a factor of at least 10 to the power of 26, and possibly far more, in an interval shorter than 10 to the power of negative 32 seconds. This rapid expansion stretched any initial quantum fluctuations to cosmological scales, smoothed out any curvature, diluted any exotic relics to undetectable densities, and took regions that had once been in causal contact, and separated them to distances far beyond what light could have traversed in the time since inflation ended. The same inflationary expansion that produced the uniform, flat observable universe also, in most versions of the theory, produced an enormous amount of space beyond what is now observable. If inflation lasted even slightly longer than the minimum necessary to produce the universe we observe, it created a volume of space vastly larger than our observable bubble. In the most common version of this picture, called eternal inflation, inflation continued in some regions while ending in others, producing a potentially infinite number of bubble universes embedded in an ever-inflating background. Our observable universe represents one such bubble, a finite region where inflation ended and ordinary physics subsequently evolved structure, stars, galaxies, and observers. Other bubbles, potentially separated from us by distances so vast they can never be crossed, may have different physical constants, different particle physics, and different histories of structure formation. The eternal inflation picture predicts a multiverse of cosmic scales that makes our observable universe, with all its 2 trillion to 3 trillion galaxies and countless sextillions of stars, a minuscule and entirely typical region within a vastly larger whole. This picture cannot currently be tested. We cannot detect other bubble universes. We have no observational evidence for or against eternal inflation's prediction of a multiverse, but it represents the honest extension of a theoretical framework that successfully explains many of the observed properties of our universe. Whether or not the multiverse picture is correct, the scale of what lies beyond the observable universe remains one of the most philosophically significant open questions in all of science. And Webb, by revealing how abundant and complex structure is within the observable universe, has made this question more vivid. If the processes Webb observes in the observable universe apply throughout a far larger whole, then the true extent of stars, planets, and potentially complex chemistry extends to scales so large that any attempt to grasp them intuitively breaks down completely. The practical work of expanding our understanding proceeds not through philosophical speculation, but through more observations, more precise measurements, and more sophisticated theoretical modeling. Webb continues to add to its observational archive. Every new deep field image, every new spectroscopic survey, every new detection of an early galaxy or high redshift black hole adds information to the dataset that theorists are working to explain. The tension between observations and models that Webb has identified is not a crisis. It is an invitation to do better science. Future instruments will extend the reach of Webb's discoveries and address new questions Webb cannot answer. The Nancy Grace Roman Space Telescope, planned for launch in the mid-2020s, will survey vastly larger areas of sky than Webb can efficiently cover, conducting statistical studies of galaxy populations across cosmic time that will reveal not just individual objects, but the overall distribution of galaxy masses, sizes, star formation rates, and chemical compositions as functions of cosmic epoch. Where Webb goes deep, Roman will go wide, mapping the statistical properties of the galaxy population from which Webb's individual targets are drawn. From the ground, a new generation of extremely large telescopes with primary mirrors spanning 30 to 40 meters is under construction at multiple sites. These telescopes, equipped with advanced adaptive optics systems that correct for atmospheric distortion, will deliver angular resolution comparable to space telescopes, while providing access to the full electromagnetic spectrum accessible from Earth's surface. Combined with Webb's space-based infrared surveys, they will enable detailed spectroscopic studies of individual early galaxies, measuring their chemical compositions, star formation histories, internal dynamics, and the properties of their central black holes, with precision impossible from current facilities. Gravitational wave observatories represent another frontier. The Laser Interferometer Gravitational Wave Observatory and its international partners have already detected dozens of binary black hole mergers and several neutron star mergers in the nearby universe. Future space-based gravitational wave observatories, like the Laser Interferometer Space Antenna, planned for operation in the late 2030s, will detect gravitational waves from supermassive black hole mergers in the early universe, directly probing the formation and growth of the monsters Webb has found unexpectedly large and early. Gravitational waves carry information about their sources, regardless of electromagnetic absorption or scattering, providing an entirely independent window into processes that would otherwise be obscured. The cosmic microwave background continues to provide information about the universe's earliest moments. Its temperature fluctuations, mapped in increasing detail by successive generations of missions, encode the primordial density variations that seeded all subsequent structure formation. Future microwave background experiments will map the polarization of this ancient radiation with higher sensitivity and angular resolution than any current instrument, potentially revealing signatures of gravitational waves generated during inflation, providing direct evidence about the energy scale and duration of the inflationary period, and constraining the theoretical models that attempt to explain how the universe began. What Webb has given us, beyond any specific discovery, is a profound recalibration of our expectations. The universe is more complex, more active in its earliest epochs, more densely populated with structure, and more surprising in its behavior than the models we developed before Webb was operational managed to predict. That recalibration is not a defeat for science. It is precisely what science is supposed to do: make predictions, test them against observations, revise the predictions when observations reveal their limitations, build more complete models, test those against new observations, repeat the process, each iteration bringing human understanding closer to a more accurate description of the universe as it actually is. The fact that Webb has found so much tension with pre-existing models means that the universe has something to teach us that we did not already know. That is precisely the circumstance that makes science genuinely exciting. A universe that perfectly confirmed every prediction would tell us we had already found the complete truth. A universe that surprises us, as Webb's universe consistently does, tells us there are discoveries still to be made, understanding still to be gained, and science still worth doing. The questions Webb leaves open will drive research programs for decades. How did the very first stars form, and what were their properties? How did the first supermassive black holes grow so quickly? What physical processes made early galaxy formation so much more efficient than the modern equivalent? What lies beyond the observable universe? How large is the full universe? Are the physical laws and constants we measure locally representative of physics everywhere? Or do they vary across the full extent of whatever larger structure contains our observable bubble? These are not small questions. They touch on the nature of physical law, the completeness of our understanding of gravity and quantum mechanics, the extent of cosmic structure, and ultimately on whether the universe is a single finite system or part of a vastly larger whole that operates by different rules in different regions. The James Webb Space Telescope did not answer these questions. It made them more urgent, more concrete, and more scientifically tractable than they were before its observations began. In that sense, Webb has done exactly what the best instruments in the history of science have always done. It has shown us that the universe is larger, stranger, and richer than we knew. It has revealed that our maps of reality, however carefully drawn, leave vast territories unexplored. And it has ensured that the science of cosmology, the study of the universe as a whole, its origin, structure, evolution, and ultimate fate, remains one of the most active, surprising, and consequential fields of inquiry in all of human knowledge. The ancient light web collects photons that began their journeys before our sun existed, carries within it the information needed to reconstruct the universe's earliest history. Reading that information, translating it into a coherent picture of how complexity arose from simplicity on cosmic scales, is the work of the current and coming generations of astronomers, theorists, and instrument builders. The universe has been patient in hiding its early history. Webb is equally patient in uncovering it, one ancient photon at a time. One aspect of Webb's discoveries that deserves deeper examination is the nature of dark matter itself, and how it interacts with the visible structures Webb observes. Dark matter is one of the most compelling and frustrating topics in modern physics. Its existence is established beyond reasonable scientific doubt through multiple independent lines of evidence. The rotation curves of galaxies show that stars in the outer regions of disk galaxies orbit at speeds that would be impossible if only the visible matter inside their orbits contributed to the gravitational pull. They orbit as though embedded in a much larger sphere of additional matter, invisible but gravitationally influential. Galaxy clusters bend light from background objects through gravitational lensing in ways that require far more mass than the visible gas and stars can provide. The large-scale distribution of galaxies in the universe matches the predictions of models that include dark matter with remarkable precision, but fails completely when dark matter is removed from the equations. Despite all this evidence for dark matter's existence, its fundamental nature remains unknown. We know what it does gravitationally. We do not know what it is. Thousands of experiments searching for dark matter particles through their interactions with ordinary matter have returned null results, ruling out large ranges of theoretical possibilities. The leading candidates for dark matter particles, weakly interacting massive particles, or WIMPs, were long considered the most theoretically appealing dark matter candidates. But extensive searches, including direct detection experiments, deep underground, and collider searches at the Large Hadron Collider, have failed to detect them. Other candidates, including axions, sterile neutrinos, and primordial black holes, remain viable, but face their own experimental and theoretical challenges. What is particularly relevant for understanding Webb's observations is the role dark matter plays in galaxy formation. In the lambda CDM model, dark matter collapses first under its own gravity, forming the halos that gravitational trap ordinary baryonic matter. The baryonic matter then cools, condenses, and forms stars within these dark matter halos. The properties of dark matter, specifically how it behaves on small scales, determine how galaxy formation proceeds in the early universe. Standard cold dark matter predicts a specific distribution of halo masses at early times, and current galaxy formation models, built on top of this dark matter distribution, produce the galaxy populations that Webb is now showing to be inconsistent with observations at high redshift. If dark matter behaves differently from what cold dark matter models assume, the distribution of early halos could be different, allowing larger galaxies to form earlier. Warm dark matter, where particles have higher velocities and therefore resist collapsing into very small structures, predicts fewer small dark matter halos at early times, but does not obviously predict more massive early galaxies. Fuzzy dark matter, a model in which dark matter consists of extremely light particles with quantum mechanical behavior on galactic scales, predicts a characteristic suppression of structure below a certain scale, but again does not straightforwardly predict the early massive galaxies Webb observes. The connection between dark matter's fundamental nature and Webb's observational surprises is one of the most active areas of current theoretical research. Whatever revision to our models of early galaxy formation turns out to be necessary, it will likely need to be consistent with what we know about dark matter from its gravitational effects, while also accommodating the unexpectedly abundant and massive early galaxy population Webb has revealed. Finding this consistency will require simultaneous progress in particle physics, in cosmological simulations, and in observational astronomy. Cosmological simulations, computer models that simulate the formation and evolution of cosmic structure from the Big Bang to the present, are one of the primary theoretical tools for understanding galaxy formation. These simulations begin with initial conditions based on measurements of the cosmic microwave background, which tells us the density fluctuations present in the early universe. They then evolve those fluctuations forward in time using gravitational dynamics and models of the gas physics, star formation, stellar feedback, and black hole growth that shape galaxy evolution. The most sophisticated current simulations can successfully reproduce many properties of the galaxy population in the modern universe, including the distribution of galaxy masses, sizes, morphologies, and chemical abundances. But when applied to the early universe, current simulations struggle to produce galaxies as massive and luminous as those Webb has detected at high redshift. The simulations do form early galaxies, but they tend to be smaller and fainter than what Webb observes. This discrepancy almost certainly reflects limitations in how the simulations model the physical processes driving star formation and stellar feedback in the early universe, where conditions were fundamentally different from the environments that have been calibrated against modern universe observations. Theorists are now working to modify and improve these simulations to better match Webb's observations. This requires understanding which physical processes are primarily responsible for the discrepancy and how to model them more accurately. Is the problem primarily with the efficiency of gas cooling and star formation in early halos? Is it with how stellar feedback suppresses star formation? Is it with how supermassive black holes form and grow, and how their energy output regulates star formation in their host galaxies? Answering these questions requires not just better simulations, but also more and better observational constraints from Webb itself on the properties of early galaxies. The observational strategy Webb uses to study early galaxies is sophisticated and multi-layered. Photometric surveys, in which Webb takes deep images across multiple infrared wavelength bands, allow astronomers to identify candidate high redshift galaxies through their distinctive colors A galaxy at very high redshift appears only in the reddest wavelength bands and is invisible in bluer bands, because the intervening hydrogen gas in the intergalactic medium absorbs virtually all photons with wavelengths below a certain threshold. By looking for objects that drop out of detection in shorter wavelength bands, while remaining detectable in longer wavelength bands, astronomers can efficiently identify candidates for follow-up spectroscopic observation. Spectroscopy, which measures the intensity of light as a function of wavelength across a continuous range, is the definitive tool for confirming redshifts and measuring physical properties. When a galaxy's spectrum is obtained, astronomers can identify characteristic emission or absorption lines from known atomic transitions and measure how far those lines have been shifted from their laboratory wavelengths. This shift directly gives the redshift, and hence the distance and look-back time. The spectrum also reveals the galaxy's star formation rate, its chemical composition, the presence and activity level of its central black hole, and many other physical properties. Webb's spectroscopic instrument, the near-infrared spectrograph, can simultaneously obtain spectra of up to about 200 objects within a single pointing of the telescope by using a microshutter array, a grid of tiny, individually controllable shutters that can be opened or closed to selectively emit light from chosen targets while blocking light from everything else in the field. This capability, unique to Webb, allows spectroscopic surveys to proceed at speeds simply impossible with previous infrared telescopes, and is one of the primary reasons Webb can build up large statistical samples of confirmed high redshift galaxies, rather than laboriously studying one object at a time. The data Webb generates is extraordinarily complex and requires sophisticated analysis pipelines to transform raw detector readings into calibrated, scientifically useful spectra and images. Corrections must be applied for the detector's sensitivity as a function of wavelength, for the transmission of Webb's optics, for contaminating light from zodiacal dust within our own solar system, and for various other instrumental effects. The data reduction pipelines developed for Webb represent enormous investments of human time and expertise, and their continued refinement is one of the ongoing challenges of the mission. Even small improvements in data reduction can reveal new signal in existing datasets, allowing new discoveries to be made from data already sitting in the archive. One of the most remarkable aspects of Webb's operational design is its Legacy Archive program. From the mission's earliest days, it was designed to make all Webb data publicly available, with no proprietary period for most observing programs. Data is released to the entire astronomical community shortly after being taken, allowing researchers worldwide to analyze Webb's observations independently and in combination. This open data policy has dramatically accelerated the pace of discovery, with dozens or hundreds of independent research groups analyzing Webb datasets and publishing results simultaneously. The breadth of analysis and the diversity of scientific questions being addressed using Webb data far exceed what any single institution or research team could accomplish alone. This collaborative model of astronomical research, where public observatories generate public data analyzed by the global research community, has become one of the defining features of modern astronomy. Webb represents this model at its most ambitious, with the world's most powerful and expensive astronomical instrument generating a continuous stream of publicly available infrared data that researchers from any institution in any country can access and analyze. The scientific output has reflected this design. Within Webb's first few years of operation, thousands of scientific papers have been published using its data, on topics ranging from exoplanet atmospheres to nearby star-forming regions to high redshift galaxy populations. The breadth of this output reflects both the versatility of Webb's capabilities and the depth of scientific problems its observations can address. The question of what Webb will find next, as it continues its planned operational life of at least 10 years and potentially much longer, is genuinely open. Its most transformative discoveries have often come from unexpected directions. The too much too soon problem was anticipated as a possibility before launch based on theoretical concerns, but the magnitude of the discrepancy exceeded most predictions. Some of Webb's most significant early findings were serendipitous, discovered in data taken for other primary purposes. Future observations will undoubtedly reveal new surprises in realms where we are currently most confident in our understanding. Among the scientific programs Webb is actively pursuing, with implications for early universe structure formation, is a systematic effort to directly observe the epoch of reionization. This is the period, roughly between redshifts 6 and 20, or between approximately 300 million and 1 billion years after the Big Bang, when the first stars and galaxies began emitting ultraviolet radiation that ionize the neutral hydrogen filling the intergalactic medium. Before reionization, the universe was opaque to ultraviolet light, as free electrons were bound to hydrogen atoms and could not facilitate the propagation of high-energy photons. During and after reionization, the intergalactic medium became ionized, allowing light to propagate freely through the vast spaces between galaxies and giving the universe the transparent character it has today. Understanding reionization is crucial for several reasons. The timing and duration of reionization constrains the number and properties of the ionizing sources, whether they were dominated by star-forming galaxies, quasars powered by supermassive black holes, or some combination. The spatial distribution of ionized and neutral regions during reionization encodes information about the clustering and properties of early galaxies. And the completion of reionization represents a fundamental phase transition in the universe, marking the end of the cosmic dark ages and the beginning of the transparent universe we inhabit today. Webb is probing reionization through multiple observational strategies. Direct detection of galaxies within the reionization epoch, confirmed through spectroscopic redshift measurements, provides a census of the ionizing sources and their properties. Measurements of quasar absorption spectra, where the ultraviolet light from distant quasars is partially absorbed by intervening neutral hydrogen, trace the distribution of neutral gas during reionization and map its progress across cosmic time. And searches for the redshifted 21-centimeter emission line from neutral hydrogen in the intergalactic medium, though not within Webb's wavelength range, are being pursued by ground-based radio observatories in a complementary effort to map the topology of reionization directly. The synthesis of information from Webb's observations, from ground-based radio surveys of reionization-era hydrogen, from gravitational wave observatories probing early black hole mergers, and from next-generation cosmic microwave background experiments measuring the polarization of the universe's oldest light, represents the future of cosmological research. No single instrument or technique will answer the full range of questions Webb's discoveries have raised, but each new observational window provides constraints that, combined with improved theoretical models and simulations, will progressively narrow the range of possible explanations for what Webb has found. The generation of astronomers now entering the field will spend their careers working with data from Webb and its successors, building the more complete picture of cosmic history that Webb's discoveries have shown to be necessary. They will do so with tools, both observational and computational, that dramatically exceed anything available to the theorists who built the models Webb is now testing. The rate of progress in both observational capability and computational power suggests that the next 20 to 30 years will see transformative advances in our understanding of how galaxies, stars, planetary systems, and the chemical elements that make complex chemistry possible arose from the simple initial conditions of the Big Bang. What we currently know, after the first years of Webb's operation, is that the early universe was far more active, far more efficient at building complex structures, and far more surprising in its behavior than our best pre-Webb models predicted. What we do not yet know is why. The gap between what we observe and what we can fully explain is not a failure of science. It is the current frontier of human knowledge about the universe we inhabit, a frontier that Webb has pushed to new locations and new depths, revealing in the process that the universe is even grander, more complex, and more worthy of study than any generation before ours had the means to appreciate. The light that left those early galaxies, more than 13 billion years ago, stretched by cosmic expansion across billions of light-years of space, collected patiently by Webb's gold-coated mirror at temperatures barely above absolute zero, processed by software pipelines into images and spectra, analyzed by researchers worldwide, and ultimately transformed into scientific papers and public understanding. That journey of ancient light, from early cosmic dawn to human comprehension, represents one of the most extraordinary achievements of scientific civilization. It is an achievement that opens more questions than it answers, and that is exactly as it should be. Among the many specific objects Webb has studied in its early years, a category called quasars, or quasi-stellar objects, deserves special attention for what they reveal about early cosmic evolution. Quasars are the most luminous, persistent objects in the universe, powered by the accretion of matter onto supermassive black holes at galactic centers. When gas falls toward a supermassive black hole, it forms a swirling accretion disk that heats to temperatures of millions of degrees through friction and compression. This intensely hot gas radiates enormous amounts of energy across a broad range of wavelengths, from radio waves through X-rays. The most luminous quasars outshine their entire host galaxies by factors of hundreds or thousands, producing as much light as several trillion suns from a region smaller than our solar system. What makes quasars scientifically invaluable for cosmological research is precisely their extreme luminosity. They can be detected at cosmological distances where ordinary galaxies would be invisible. The most distant quasars known, discovered through surveys that predated Webb and now being studied in unprecedented detail with Webb's spectroscopic capabilities, exist at redshifts exceeding 7, placing them at distances corresponding to when the universe was less than 800 million years old. A handful of quasars have been discovered at redshifts approaching 9 or 10, corresponding to the universe's first 500 million years. These early quasars are profoundly puzzling. Their luminosities imply that the black holes powering them already have masses of hundreds of millions to billions of solar masses. As discussed earlier, building a black hole that massive in a few hundred million years is extremely difficult to explain with standard physics. But quasars add another dimension to this puzzle. Not only are their black holes unexpectedly massive, they are unexpectedly luminous in ways that tell us about the rate at which their black holes are currently consuming surrounding matter. The combination of black hole mass and accretion rate observed in high redshift quasars is challenging to explain with any simple model of black hole growth. Webb's spectroscopic capabilities are being used to study the spectra of high redshift quasars in detail that was previously impossible. By measuring the widths of emission lines in quasar spectra, astronomers can estimate the masses of the black holes producing those lines through a technique called reverberation mapping and related methods. By measuring the overall luminosity and the shape of the spectral energy distribution, they can estimate the accretion rate. By looking for absorption features in quasar spectra produced by intervening gas at lower redshifts, they can probe the distribution of matter along the line of sight. And by searching for the host galaxies surrounding high redshift quasars, they can study the relationship between the most extreme early black holes and the galaxies in which they are embedded. Early results from Webb studies of high redshift quasars have confirmed that these objects are even more extreme than ground-based spectroscopy had suggested. The black holes powering the highest redshift quasars are indeed extraordinarily massive for their cosmic epoch. The host galaxies of some high redshift quasars, now detectable in Webb's infrared images in cases where they could not be separated from the quasar light in previous observations, show evidence of intense star formation, suggesting a close connection between early black hole growth and early galaxy building that current models do not fully explain. The relationship between supermassive black holes and their host galaxies, observed across a wide range of redshifts, provides one of the most important clues about how galaxies form and evolve. In the modern universe, the masses of supermassive black holes correlate tightly with the properties of their host galaxies, particularly with the mass of the galaxy's central stellar bulge. A galaxy with a more massive bulge has a more massive central black hole, in almost perfect proportion. This tight correlation persists, even though the black hole occupies a region millions of times smaller than the bulge, and the two seem to have no direct physical mechanism for exchanging mass. The correlation strongly implies that something fundamental about galaxy formation regulates both the star formation that builds the bulge and the accretion that builds the central black hole simultaneously. This coevolution of galaxies and their black holes is one of the most active research topics in observational and theoretical astrophysics. Webb is observing this coevolution at the earliest epochs where it can be studied, determining whether the tight correlations seen in modern galaxies already existed in the early universe, or whether they developed later as galaxies matured. Early results suggest that the relationship between black hole mass and host galaxy mass may have been different in the early universe, with some high redshift quasar host galaxies appearing less massive than the local scaling relations would predict for their black hole masses. If confirmed, this would imply that supermassive black holes grew faster than their host galaxies in the early universe, with the galaxy catching up in subsequent billions of years of star formation. Understanding when and how the coevolutionary relationship between galaxies and black holes established itself is important for understanding the overall history of galaxy formation. The energy released by accreting black holes, the quasar mode of feedback, is thought to play a major role in regulating star formation in massive galaxies. When a supermassive black hole is actively accreting at high rates, the radiation and jets it produces heat and expel gas from the surrounding galaxy, shutting down star formation. This mechanism, called AGN feedback, where AGN stands for active galactic nucleus, is invoked in theoretical models to explain why the most massive galaxies in the modern universe have old stellar populations and low current star formation rates, despite having the deepest gravitational potential wells that should be most effective at retaining gas. If AGN feedback operates in early galaxies as the models assume, then the rapid growth of supermassive black holes in the first few 100 million years would have had profound effects on early galaxy evolution, potentially explaining some aspects of the rapid early star formation and subsequent quenching that Webb appears to be observing. But the details of how AGN feedback operates, how efficiently it drives gas out of galaxies, over what timescales, and how its effects depend on galaxy mass and black hole mass, remain poorly understood. Webb's observations of early galaxies in various stages of activity and quenching are providing new constraints on these processes at redshifts that previous instruments could not probe. The interplay between galaxy formation, star formation, chemical enrichment, and black hole growth creates a complex web of interconnected processes spanning a vast range of spatial and temporal scales. Stars form on scales of fractions of a light year. Galaxies extend across tens of thousands of light years. Galaxy clusters span millions of light years. The cosmic web of filaments and voids extends across hundreds of millions of light years. Processes operating at each of these scales influence what happens at the others. Stellar feedback from individual stars affects the conditions for star formation in their surrounding molecular cloud. The collective feedback from all the stars in a galaxy affects the galaxy's overall star formation rate. The clustering of galaxies into groups and clusters influences the availability of fresh gas for continuing star formation. The large-scale cosmic web channels matter from low-density voids into high-density filaments and cluster cores, continuously supplying the raw material for galaxy formation. Understanding this multi-scale hierarchy of processes, from the physics of individual stellar nurseries to the dynamics of the cosmic web, is the central challenge of modern observational and theoretical cosmology. Webb contributes to this understanding primarily by providing observational data about the early stages of this hierarchy's evolution, when the processes were operating in conditions fundamentally different from those we observed locally, and when the outcomes were, as Webb has now shown, different from what our models predicted. The significance of Webb's contributions extends beyond any specific discovery to the general question of how science advances when observations challenge established theory. The history of science is filled with examples where careful observations revealed that an established theoretical framework, however successful it had been, was incomplete or incorrect in some domain. Newtonian gravity, extraordinarily successful at describing planetary motions and terrestrial mechanics, turned out to be an approximation valid only at low velocities and weak gravitational fields, superseded by Einstein's general relativity for situations involving high velocities or strong fields. Classical electromagnetism, beautifully unified by Maxwell's equations, turned out to be a classical approximation to quantum electrodynamics at scales where quantum effects matter. The standard model of particle physics, successful at describing the interactions of subatomic particles to extraordinary precision, is known to be incomplete because it cannot incorporate gravity or explain dark matter or dark energy. In each of these cases, the limitation of the established framework was revealed not by pure theoretical reasoning alone, but by observations or experiments that fell outside its domain of successful prediction. The observations forced theorists to think more carefully about the assumptions underlying existing models and to develop more complete frameworks that could explain both the original successes and the new observations. The resulting theories were not just patches on the old ones. They represented genuinely deeper understanding that unified previously separate domains and made new, testable predictions. Webb's observations of the early universe may be pointing towards something analogous in the domain of galaxy formation and cosmology. The Lambda CDM model, with its current treatment of galaxy formation physics, is extraordinarily successful at describing the modern universe. Webb's observations reveal its limitations at high redshift. Those limitations will drive the development of more complete models that can explain galaxy formation across all cosmic epochs, not just the period when the universe has already matured. Whether those improved models will require new physics, new treatments of known physics, or simply better numerical implementations of existing equations, remains an open question that Webb's ongoing observations are actively constraining. Whatever the resolution turns out to be, the universe Webb is revealing is demonstrably richer, more active in its early history, and more surprising in its structure than the universe our pre-Webb models described. That is reason for genuine scientific excitement. It means there are important things about how the universe works that we do not yet understand. It means significant scientific discoveries remain to be made in the coming years and decades. It means that the field of cosmology, far from approaching completion, is at one of its most intellectually productive and genuinely open moments. The James Webb Space Telescope has not answered the deepest questions about the universe. It has sharpened them, made them more concrete, and provided the observational foundation needed to pursue them with scientific rigor. The ancient light it collects carries information from the universe's earliest epochs, a cosmic archive written in photons that have been traveling since before Earth existed. Reading that archive, understanding what it tells us about how the universe built complexity from simple beginnings, and reconciling those readings with our theoretical understanding of physical law is the work that now lies ahead. It is work that the generations of astronomers, physicists, and computational scientists now entering the field will carry forward, building on Webb's foundation toward a more complete understanding of the universe we inhabit and how it came to be. Final character count confirmation. There is one further dimension of Webb's discoveries that deserves careful attention, and that is the philosophical and human significance of what it means to observe the universe at these depths. Science is often described in purely technical terms as a method for generating reliable knowledge about the physical world through observation, hypothesis, testing, and revision. That description is accurate as far as it goes, but it understates something important about the human experience of doing science at the frontier of knowledge. When Webb detects light from a galaxy that formed 300 million years after the Big Bang, it is not merely collecting photons and running them through detectors. It is recovering information that has been traveling through space for 13,500 million years. Information that encodes a moment in the universe's history that occurred before our planet existed, before our star existed, before the interstellar gas from which our star would eventually form had even been enriched with the heavy elements necessary to build rocky planets. The galaxy whose light Webb detects is gone. It has merged with other galaxies. Its stars have aged and many have died. Its gas has been consumed or expelled. The universe has evolved beyond recognition from what it was when those photons departed. And yet, the photons survived. They traveled through 300,000 kilometers of space per second, through billions of years of cosmic expansion, through the vast empty spaces between galaxies and across the growing distances produced by the universe's accelerating expansion. They arrived at the second Lagrange point, were collected by Webb's gold-coated mirror operating at temperatures barely above absolute zero, converted into electrical signals by arrays of infrared-sensitive detectors, transmitted to ground stations on Earth, processed by software pipelines, and ultimately transformed into numbers that researchers turned into images and spectra and scientific papers read by human beings. That entire chain, from the emission of photons by hot gas and young stars in an ancient galaxy to the reading of a scientific paper in the present day, represents a remarkable continuity of information across time. The universe, through the mechanism of light, provided us with a record of its own early history. We built instruments sensitive enough to read that record. And in reading it, we found that the universe's early history was more complex, more active, and more surprising than we had anticipated. This capacity to recover information from the universe's past and to be surprised by what that information reveals is one of the most distinctive features of scientific inquiry. It is also, in some sense, one of the most humbling. The universe does not care whether its behavior matches our theoretical expectations. It behaves according to physical laws that were in operation long before any observer existed to study them. When our models fail to predict what we observe, the fault lies not with the universe, but with the incompleteness of our models. The universe is always right. We are always catching up. Webb has made the catching up process more concrete and more urgent in the domain of early universe cosmology. The discrepancies it has revealed between observation and theory are real, significant, and not easily explained away. They demand serious theoretical attention and will likely require genuine advances in our understanding of how galaxies form, how black holes grow, and how the efficiency of cosmic structure formation depends on the conditions prevailing in the early universe. Those advances will come through the combination of better observations, better theory, and better computational models working together in the iterative process that defines scientific progress. The universe revealed by Webb, 2 trillion to 3 trillion galaxies in the observable portion alone, ancient galaxies assembled with surprising speed and efficiency Supermassive black holes grown to impossible sizes in improbably short times. All of cosmic history, encoded in the wavelengths of ancient light now detectable for the first time through Webb's infrared eyes, is a universe worth understanding. Its scale challenges our intuitions. Its early complexity challenges our models. Its beauty, in the sense of the intricate order underlying its apparent chaos, rewards careful study. The ancient photons Webb collects have waited 13 billion years to be understood. Scientists are only beginning to read what they carry. The story of how humanity learned to look backward through time, from Galileo's first telescopic observations of Jupiter's moons, to the Hubble Space Telescope's revelations about an expanding universe, to Webb's detection of galaxies, formed just hundreds of millions of years after the Big Bang, is one of the most extraordinary intellectual journeys in history. Each generation of instruments has extended the reach of human perception into domains previously inaccessible. Each extension has revealed that the universe is larger, older, more complex, and more surprising than the instruments of the previous generation could show. Webb is not the end of this journey. It is the most advanced waypoint reached so far. The questions it raises about early galaxy formation, early black hole growth, the efficiency of early star formation, and the true extent of cosmic structure will motivate the design and construction of the next generation of instruments. Those instruments will see deeper, measure more precisely, and access wavelengths and phenomena that Webb cannot reach. The surprises Webb has delivered suggest that the next generation will find its own surprises, things the current generation cannot anticipate precisely because our current understanding is incomplete. That is the nature of scientific inquiry at the frontier. Each advance reveals not just answers, but better questions. Each instrument not only confirms what was predicted, but reveals what was not. The universe is genuinely surprising, and our collective scientific project of understanding it is genuinely ongoing. Webb has made it more surprising and more urgent in equal measure. That combination, surprise and urgency in service of understanding, is exactly what drives science forward. The ancient light still arrives. We are still learning to read it. There is something worth pausing on about the specific way Webb detects these ancient objects. Infrared light, the kind Webb is designed to capture, is invisible to human eyes. We experience infrared radiation as warmth, as the heat we feel from a fire or the sun, but we cannot see it. Webb sees an entirely different universe than any human eye has ever perceived. Its gold-coated mirror reflects wavelengths of electromagnetic radiation that pass through our visual experience without registering, wavelengths that carry information from the most ancient observable galaxies precisely because they have been stretched from visible and ultraviolet wavelengths by billions of years of cosmic expansion. In a very real sense, every image Webb produces is a translation. The infrared signals that Webb's detectors register are converted into the visible light images that human researchers examine on their screens. The colors in those images are not real colors in any visual sense. They are representations, scientific codes that map different infrared wavelengths to visible colors so that human researchers can interpret spatial and spectral information that their eyes could not otherwise perceive. The breathtaking images of early galaxies, of nebulae, of galaxy clusters that Webb has released publicly are real data, precisely rendered in a form human visual systems can process. They are accurate representations of real infrared emissions, but the universe does not look like those images to any hypothetical observer capable of perceiving it directly. The universe, at those distances and in those wavelengths, is invisible to any instrument tuned to human visible wavelengths. This translation from the invisible to the visible is itself a profound act of scientific interpretation. It is one of the ways that science extends human perception beyond its biological limits, allowing us to access and understand aspects of reality that evolution never prepared us to observe directly. Our biology equipped us to navigate a small patch of a single planet orbiting a single star in one galaxy among 2 trillion others. Science, through instruments like Webb, extends our perceptual reach to encompass the entire observable universe and its 13.8 billion year history. That extension is one of the most remarkable achievements of collective human intellectual effort. Webb continues to observe. Every day, it gathers new photons from ancient galaxies, building an archive of early cosmic history that future researchers will mine for decades. Every survey it completes adds data to the growing tension between observation and theory, adding constraints that models must eventually explain. Every confirmed high redshift galaxy adds a data point to the statistical picture of how cosmic structure assembled itself in the universe's first billion years. Every spectrum obtained reveals more detail about the chemical composition, star formation history, and black hole activity of early galaxies, providing the information needed to test and refine theoretical models of how those properties evolved. The scientific community processing Webb's data is global, drawing on researchers from dozens of countries working across multiple institutions and disciplines. Cosmological theorists, computational astrophysicists running large-scale simulations, observational astronomers designing and executing Webb programs, spectroscopists measuring galaxy properties, and data scientists developing analysis pipelines all contribute to the collective project of translating Webb's raw data into scientific understanding. This collaborative, international nature of modern astrophysics is itself a reflection of the scale of the scientific problems being addressed. No single researcher, no single institution, and no single nation has the resources, expertise, or perspective to address these questions alone. The universe is a shared challenge, and understanding it is a shared project. That sharing extends to the public. Webb's most striking images are released not only in scientific journals, but in formats accessible to anyone with an internet connection. The public fascination with Webb's images, visible in the millions of shares and discussions that follow each major image release, reflects something genuine about human curiosity. People who have no particular investment in the technical details of infrared spectroscopy or high redshift galaxy surveys nonetheless respond to the sight of thousands of galaxies in a patch of sky the size of a grain of sand, or the detection of a galaxy that formed just 300 million years after the Big Bang. The scale of these discoveries resonates at a level that transcends scientific specialization. Part of what makes these images and discoveries resonate is the simultaneous sense of vastness and connection they convey. The universe is extraordinarily large and extraordinarily old, populated by structures of mind-bending complexity. And yet all of it, every galaxy, every star, every planet, every atom, and every living thing on Earth, traces its origin back to the same primordial conditions of the Big Bang. The hydrogen in every star, in every one of those 2 trillion galaxies, is the same hydrogen produced in the first few minutes of the universe's existence. The heavier elements in every rocky planet, in every planetary system, were forged in stars that lived and died before those planets formed. We are made of material that has been through stellar interiors. We are part of the universe's ongoing process of organizing matter into increasingly complex structures. Webb makes this connection visible in a new way by showing us what the beginning of that process looked like, how complex structures first assembled themselves from primordial simplicity, faster and more abundantly than we expected, and how the universe's capacity for organization was present and active from its earliest observable epochs. The story Webb is helping to tell is not just the history of galaxies and black holes. It is the history of everything, including us, traced back to its earliest readable chapter. And that story, it turns out, is richer and more surprising than we knew.